started just so we can kind of keep on schedule, and I'll let Zach take it away from here.
Hi guys, so this is basically, I'm going to be talking about quantifier elimination in Maple, a new package I'm developing. This is basically the main driver, if you like, behind my PhD project. It's a majority of it, I suppose. Supervised by James Davenport, University of Bath. He'd love to be here, but knowing James, he's at 10 conferences already today. So yeah, let's get started. I'll talk to you about what I'm going to talk about. So I'll give you an overview to start off with about the two of the main sort of algorithms, if you like, for doing QE, VTS and CAD. Two very popular ones. We've seen a lot of CAD already, which doesn't mean the Canadian dollar, unfortunately. I'll talk about the package I'm actually building, some of its features, and what it really intends to do in contrast to what's already sort of on the market, if you will. And then I'll sort of show you some preliminary benchmarks from under the hood. In particular, I'll show you a demo of how the package really works in Maple, so remind me to do that if I don't for some reason. And yeah, I'll just close out after that. So let's get right into it. So quantifier elimination hasn't been explicitly talked about so far. We've seen a lot of CAD, but this is really one of the main reasons to do CAD. So if you have a quantified statement of polynomials, so you've got a string of quantifiers, I have m of them, and then a formula over x1 to xn, so you've got n variables. You've got at most as many quantifiers as you have as variables. And then phi is a Tarski formula. So this is a Boolean combination of polynomial constraints, which is quantifier free. You've got all your quantifiers in the front. So I'm only allowing operators and an or. And those relations there, so you've got less than and less than or equals to, blah, blah. That's just because Maple uses those without loss of generality, really. And then the idea of quantifier elimination is to eliminate the quantifiers. So you're either going to get a Tarski formula over the variables that are left if you had some free variables, perhaps, or you might get true or false, and you'll definitely get true or false if everything was quantified. And I've lied a little bit because what I've really just described is a pre-next formula. Pre-next formula basically means just a string of quantifiers before something which is entirely unquantified, and your formula only has and or. So in general, a non-pre-next formula would be one where you have quantifiers distributed somewhere within Boolean operators, and also you can allow things like implies and not as Boolean operators as well. So all the formulae I'll show you are pre-next, but all my software can deal with, my package can deal with non-pre-next in most cases. So why do you really want to do quantifier elimination? Well, this is going to be a little bit of a weird example, as it were, but I want to show you that you could really pose a lot of things as quantifier elimination problems. And especially I want to say that I think people avoid using quantifier elimination quite a lot because it has some deficiencies, but because the algorithms so far are so hefty. So this is a little bit of a weird one. This is one from engineering, basically. There's a guy who wrote a paper on engineering problems as QE problems. But in general, these examples come from all over the place: algebraic geometry, economics. We had a paper on that last year talking about doing economics problems as QE problems. So here we've just got a box with 3 forces on it, and we want to talk about the resultant force N on this box from F1, F2, and F3. And so those are F1, F2, and F3. They're functions of P, basically. And I want to work out N. I want bounds for N, N1 and N2. And I want to eliminate for all P. So for all P in that range, I want N to be bounded between N1 and N2, and I want to talk about N1 and N2. So this is a really weird application to QE. It's completely linear. So something like linear programming or something like that would probably be better for this. So I'll embarrass myself later by doing this problem via my kit, and that will demonstrate one of the deficiencies of VTS as it is, actually. But yeah, so these things can crop up everywhere. So let's get into VTS. This talk shouldn't be too technical. I don't want to overwhelm you. If you do understand VTS or CAD and you didn't already by the end of the day, then come talk to me, but I can't offer you a job. So VTS is really a concise method, is really what I want to get across here for doing QE. So it really deals with one quantifier at a time. I'm talking about this in particular because CAD really contrasts the VTS in what I'm talking about here. It does one quantifier at a time, and it produces further formulae. It deals entirely with formulae. So these implicitly quantified formulae that you get are things that you can propagate QE on however you like, more VTS or CAD. So that's a real big point for my project. So the idea is really to eliminate a quantified variable. You want to look at all the polynomials in your formula, in all the constraints, and you want to substitute a point from each interval of a real line implied by every polynomial in the quantified formula. So these polynomials are really defining intervals, and I want to hit every interval. But that's really weird, because so I'm really viewing these polynomials as recursive polynomials here, and if I'm doing that, then the coefficients of these polynomials describe the roots, the root expressions for that polynomial, but these coefficients are polynomials in themselves. So these points I'm trying to substitute aren't even rational numbers. They're going to be polynomial expressions, right? Sorry about this clicking sort of thing. So this is why we really call it virtual substitution, and the virtual and virtual substitution is sort of hard to understand, hence why if you understand it by the end I'll give you a medal. But so this is really what things look like, and don't panic if you're like me in your undergrad, you didn't like analysis. That you've got infinitesimals here, you've got epsilon and you've got infinity. These aren't real infinitesimals really, so another part of virtual substitution is really how you deal with substituting infinity and expressions involving epsilon, right? So this 2 plus epsilon here really came from this polynomial over here, where I need to substitute something just to the right of 2, right? So that epsilon really just means some small amount which I don't know yet, because that polynomial, well, in this case is pretty trivial, but in general, if it had more complicated coefficients, I wouldn't know really what that amount is yet, because I'm not doing back substitution here. I'm immediately trying to substitute as is. So that's where that epsilon comes from. This second point here, so I've got, if I'm viewing this polynomial here as something in y, then this polynomial isn't even something in y if z is 0. So this part here, if z is not 0, is what we call a guard. So that's why this appears down here. So once I do the virtual substitution, and I know the result of that, I have to guard that with z is not 0 to make sure that's even a valid substitution. So these formulae these substitutions would really expand into something pretty nasty, which I can't fit onto one slide as is. In fact, those formulae would expand into something that look pretty silly, because VTS really relies on pretty good simplification. And the only other point to mention here is that you've got a for all x right at the front there. So that's what I mean about you're eliminating one quantifier at a time, and you get something implicitly quantified. And I could even distribute this for all x in front of whatever I like, in fact. So that's a little bit of intuition as to what it does. Mostly what we're interested in here is the pros and cons. So here are some pros. You got that it largely ignores unquantified variables. So they just sort of get mushed around in what you do with a substitution. You got tons of scope of strategy, which I've barely scratched the surface of, really, in terms of what you do and what test points you pick, etc. Best case is extremely fast. So if you have something completely existentially quantified, for example, the best case is that you have m quantified variables and you do m substitutions, one for each variable, and bam, you get an answer. That's really quick. I haven't explicitly said it, but VTS should be very good at linear examples, because linear, substituting from a linear polynomial is just, b over 8. Yeah, so as I keep saying, this is a real big, part of my project, is that it eliminates one quantifier at a time, and you get further QE subproblems. So, this is a recursive process, if you want to call it that. And again, as I've said before, it's really quite dumb in the sense that the formulae that it can produce can look quite silly, very unsimplified. And here's the big thing as well, it's degree limited. We can't do this for every problem because you have to have, to eliminate a quantified variable x, you have to have the x appears at most cubically, right? That's after factorization, so VTS can do some factorization, factorize into cubics or less, and then deal with it. But basically, degree limited up to 3, and highlighted in red is the real important point. So I apologize to the reviewers who had to see the first version of this tree. It was an abomination. What I wanted to do was zoom in a little bit. Will this work? Maybe not. Ah, cool. I've zoomed in a little bit. I wanted to zoom in more, but it's not letting me. Anyway, get your binoculars out. We'll have a look. What I think is very understated, really, is the VTS, multivariate VTS. So this is understated entirely in VTS literature. Forms a tree structure, right? Which isn't hugely surprising, but really the point is that every branch, every edge of the tree is a substitution point, and then you get a load of nodes, right? So these nodes, so that G is the guard that I was talking about before, so that would be like the Z is not 0 that I mentioned before, and then you get you conjunct that with the result of substitution, and importantly, so I've asserted that the last quantifier here exists, and then the one before that is for all. And importantly, elimination of an existential quantifier forms a disjunction at that level. So you get a disjunction here, and then I've got all the previous quantifiers in front, quantified variables in front, right? And then beyond that, when I do the for all, I get an implicit, well, not an implicit, an explicit conjunction within that. So I'm forming here a conjunction within a disjunction, and that's because basically VTS and existential quantifiers, basically you're looking for examples which work, and then for eliminating a universal quantifier, you're eliminating, you're looking for valid counterexamples, hence why you have some negation going on down here, right? So this is a little bit complicated, but either way, moral of the story is you get a tree structure, right? There you go. Moving on, so in terms of how it's implemented, lends itself very well to an object-oriented implementation, so that's what I do. So each node is basically an object. And then pseudo-remainders are really the main driver in terms of how virtual substitution works. You got lots of building of formulae, so from the material I just mentioned, if you want the quantifier-free output by the end, you have to build the formula coming from that tree. And then even the results of virtual substitutions, each individual formula, you have to build those. Lots of formula building. Benefits from very good formula simplification because it's really dumb, the formulae that it produces by standard. So moving on to the Canadian dollar. So you got, the idea is that you produce a sign invariant decomposition of Rn into cells. So Dorian was talking about this earlier, so I won't go into it too much, but I will show you a CAD. The idea is if every cell is sign invariant for your every polynomial from a formula, then it's truth invariant for the formula, right? So then you can actually deduce the quantifier-free equivalent of your QE problem. And you have to iterate this projection operator, which is really hefty. So you have your k variables, and then you use the projection operator to get k minus 1 variables. You keep doing this until you get univariates. And then from these univariate polynomials, you can isolate the roots of that, and you're going to do something like a back substitution process, but not entirely back substitution because these aren't equations really. You want to isolate the roots of these univariates and then substitute exactly the roots of those univariates and everything in between, right? Hence why you get all sorts of cells. So the idea is that this projection operator should be sufficient to produce meaningful polynomials at each level. Which means something in terms of your problem. So that's what I just described. So this isn't actually CAD, this is an AD, algebraic decomposition. So you got S1 is everything outside the circle, S3 inside, S2 the circle itself. So those all have different signs. Here I draw some lines, and now it's a CAD. There's some colors. So now what you've got is that if I take any two cells, right, so if I take this cell here and this cell here, project downwards onto the x-axis, I get something completely disjoint, right? But if I take, say, S35 and S33, project down onto the x-axis, I get exactly the same thing in terms of that subset of the x-axis, right? So that's called cylindricity. That's these cells are cylindrically arranged, and that's actually how you process alternating quantifiers, really. So if I extend that to be the circle and a line as well, so you've got x squared plus y squared less than 1 and 2x less than 1. CAD just gets the set of polynomials from that formula, right? So it sees no Boolean structure whatsoever. We're going to project from x and y onto just polynomials and y. You get those, and that's the discriminant and resultant. So those are operations you want to take in order to deduce some geometry. Excuse me. And from that, you get a couple meaningful points. Well, 4 meaningful points. I'm trying to zoom in. It's not working. You get 4 meaningful points. So you got the edge of the circle, point there that shows you the intersection of the line with the circle, and then the same on the other side of the y-axis. So that's really the idea behind projection and why it's needed. So pros and cons of CAD. It's a complete algorithm. It works for any degree, unlike VTS, which is only works up to degree 3. It's had lots of research over the years because it's complete, almost really. So it's popular in the sense that it's complete. So it's had lots of research done on improving projection, trying to make things faster. Very often implemented. There's quite a few implementations. You have to dig around in all the unquantified variables. You have to build CAD over space for unquantified variables, which VTS doesn't really need to do. And it's a bit of a sledgehammer because you may end up with your projection. You might end up deducing geometry which wasn't really meaningful to your problem at all. Partially because CAD isn't seeing any of that Boolean structure at all. Doesn't care about it. So there are some examples where CAD is really bad compared to how obvious a problem is almost. It's also very sensitive to the number of variables, incredibly. Is a con that I didn't mention on that slide. So again, you get a sort of similar tree structure from when you actually build these cells. So it's similarly object-oriented. Uses root finding, for any room associated with that. For a real root isolator and lifting, this is my new implementation I'm talking about. So resultants and discriminants and operations like that are sort of a main driver, if you like, in terms of polynomial operations. And so this new implementation in particular implements some latest research on CAD, implements a Lazard projection, one of the first, or maybe the first, definitely the first in Maple to implement Lazards. This is the best sort of contemporary projection operator, if you like, which takes you from polynomials and k variables to k-1 variables, and in particular, so it includes some tentative support for equational constraints. James Davenport back in Bath and his other student Akshar, they work a lot on that. They're trying to prove the validity of equational constraints, which I won't go into too much for Lazard projection. So currently, it tentatively includes that. It might not completely make it to release. We'll see. So quantifier elimination is slow. Worst case, double the exponential number of variables. So we need to speed this up. So reasons why, basically, projection CAD, you're taking resultants of resultants, discriminants of resultants, blah, blah, blah. Polynomials just blow up in size completely. Virtual substitution, meanwhile, ideas as to why this is slow is if you're dealing with quadratics, stuff like that, you can double the degree of the formulae per iteration, and also the size in terms of the number of atoms is increasing as well. So it's slow. So we're focusing on speed improvements, better projection operators. I'm implementing one of the better ones. Lifting improvements. So partial CAD, for example, is you stop building your tree once you know that you've solved or you have the quantifier-free output for your QE problem. You don't need to build anymore. So my implementation is also partial, is something I should have mentioned. And thank goodness for Marek Costa. I spent about a year staring at his thesis until I worked out more about VTS. He delineated how you do cubic virtual substitution. So let's talk about the competitors. So there's QuepCAD B, or just QuepCAD, done by Chris Brown. It's something you can compile and install yourself. It's an interactive sort of QE application. It's a little bit clunky, fairly old now, but that does partial CAD in particular. You've got regular chains of Maple. So that's shipped natively with Maple. Doesn't use the Lazard projection, but that'll do just CAD. Synrac, associated with Fujitsu, just implements VTS. So that's pretty notable for me. Mathematica implements VTS and CAD and some other stuff. And then you've got Redlog for reduce, same thing, VTS and CAD. So these last two are pretty important for me. I'm implementing both VTS and CAD concurrently, but what I want to convince you of is that I'm doing something different to them. My best guess is what they do is that they don't do anything similar to what I'm looking to do. So I'll explain that in a moment. So quantifier elimination, this is the package that I'm building. It investigates a poly algorithm, which really essentially means hybrid, but James doesn't like the word hybrid for this. I guess I see why. Between VTS and CAD, and it's not just designed, or it's not just aiming to be faster. I want to provide rich output and lots of strategy options for QE. Right? I want to make this a good package in terms of a mathematical toolbox. Right? So it's going to be comprehensive. Really, the idea behind this poly algorithm is that VTS is powerful and concise, but it's limited in what it can do. We can't do anything above cubics, right? If we can't factor into cubics and less, we're sort of screwed. So CAD, can we use it? Sorry. There you go. Can we use CAD intelligently to overcome those limitations? Is really the idea. So the idea is to use VTS as far as possible. So you can commute similarly quantified variables, so that gives you some scope for variable strategy, to eliminate variables of least degree first, essentially. So that's sort of your greedy variable strategy. And then you get this tree structure, and then these tree structure, these nodes are basically implicitly quantified QE formulae, right? So you're going to get more QE problems, which you want to use VTS on. But if you can't factor into degree three and less, right? Then you have to use CAD and do some root isolation and all that on a choice node, right? So you're doing just CAD on one node at the moment, right? So my best guess as to what Mathematica and Redlog do is that they actually collapse. Where's my tree? There it is. They'll actually collapse the whole tree. Basically into one QE formula, and then they'll do CAD on that whole formula, right? What I'm trying to do instead is I'm trying to say, okay, there's a node down here, right? Maybe a really deep node, right? Which has very few variables to it. CAD is really sensitive to the number of variables. So if I can isolate a node, say, right, I'm going to do CAD on just that to solve the QE problem there, and then that gives me the quantifier-free output, and you're done, that's a really good best case, right? So you use CAD on a choice node, but say that doesn't give you the answer immediately. Well, what you're going to do is you're going to use incremental CAD, and I'll explain what incremental means belatedly in a moment, to solve the implicit QE problems for further nodes if necessary. Right? So, okay, if your first CAD didn't work, then you can extend upon that CAD, build a master CAD, and basically the idea is that a CAD on one set of polynomials is sign invariant for the set you started with. So if you take a set, do a CAD for it, extend that set, still sign invariant for all those polynomials. So it solves both QE problems that you sort of wanted to put in. So the implications of this, what is really the best strategy for ensuring we can use VTS as long as possible, right? I want to do as much VTS as possible. There's some quite non-trivial questions in terms of variable strategy there. And there is a problem in terms of the fact that traversing the tree depth-wise, which really makes sense, I guess, in terms of getting to an answer maybe as quickly as possible for something completely existentially quantified or similar, it's going to fix the variable ordering for all those partially eliminated variables for VTS or otherwise. And more implications for the next two parts. So you're building a master CAD, and I'll explain what incremental more in a minute. But you're trying to build this master CAD incrementally. But this is really good, right? Because of this lemma that I showed you here, this lemma, it's really good if I don't have to extend this CAD much, because these VTS nodes had really similar polynomials, right? So if I start with this one, do a CAD on that to solve the QE problem there. Didn't give me a QE answer, a quantifier-free answer overall. Fine. But I moved to this node over here. And because VTS is so sort of dumb, actually the polynomials as part of this node were pretty similar to ones over here. So I don't have to do much extending on my CAD. I don't have to spend a lot more work, right? But perhaps, I really hope it's the case, I haven't found out yet, perhaps it's the case that actually you don't have to expend a lot more work to do this process, so this sort of hybrid QE, right? So yeah, and CAD is very sensible to the number of variables and inputs, so I really want to probably traverse depth-wise, do CAD on the QE problem with the least number of variables possible, and then maybe that's a really good best case, right? So quantifier eliminate is a part of quantifier elimination, which does this poly algorithm between VTS and CAD. If you really want to upset me and ignore my life's work, then you can use good old partial CAD, and that'll do the same thing. It'll do QE via just CAD instead, no VTS. And you know, these functions accept as little as a quantified formula. You just put one formula in. You don't need to give it a variable ordering or anything like that, or tell it about any strategy. It'll have defaults, right? But you can customize the strategy if you want. And yeah, the CAD implementation is the first to implement some contemporary research. Yeah, so the features and aims. So the output in particular, it depends on how many output arguments you request, really, right? So at the very least, if you call it with no arguments or just one argument, you just get the quantifier-free formula, right? And then if you ask for two, you get something called a list of witnesses. So this is an idea which I think originally I inherited from regular chains a little bit. So the idea is that, okay, you do your QE problem and you get out true, right? But what's the proof of that, right? So say it was a completely existentially quantified problem. The idea is if I eliminate an existential quantifier, that implies an assignment, right? That if I assign all these variables to something, I should get true for the original formula, the unquantified part. So a list of witnesses is basically a list of assignments of quantified variables proving that equivalence to true or false, right? So if it was completely universally quantified, then the idea would be you get a list of counterexamples, right? And then lastly, if you ask for free output arguments, you basically get an object back which you can pass into other routines to extend upon this QE result in some way. So I think, no, not yet. I will belatedly explain about insertion, deletion, and extension of a QE problem. So in this paper associated with this talk, I covered production of witnesses. It's basically extending a bit on Marek Kosta's work because he didn't really define this process rigorously. But basically, you get these witnesses and actual real numbers for these variables from a back substitution sort of process. And another part of this output is that if there are any sort of VTS tree nodes which I didn't end up doing any QE on, they should really be given back to the user, right? So the user can evaluate those subproblems that weren't evaluated if they so wish. And all these procedures make use of Maple's info level, which is basically if you want to print extra information about how the problem was solved, then these routines use that. So now I will belatedly explain what an evolutionary technique means. So for me, I use the word evolutionary because incremental and decremental should mean different things. Incremental means so you do QE on an original problem, and then you want to add some more constraints, right? You want to insert some formula into the original formula you did QE on, but you reuse the data structures that you already used for your first problem, right? So this is evolutionary, but here many people use incremental to mean both incremental and decremental. I don't like that, so here I use the word evolutionary. And there are some of those in quantifier elimination. So there's insert formula and delete formula, where you can insert and delete formula from an original result, and I'll explain why that's a little bit desirable soon. And the output semantics of those are exactly the same as quantifier eliminate. And so this is designed to be most useful where you start, and QE is fairly hefty potentially, right? So you start by asking, okay, does there exist you basically solve the SMT problem, a full existence on a set of assumptions, right? So you check if the assumptions are even satisfiable, right? And then you can extend that with the hypotheses once you know that that's even a reasonable question, right? So you basically insert the formula corresponding to your hypotheses somewhat, making sure that it fits that implies. So this is sort of this formulation came up in economics especially is where I sort of got to like this idea from. And these evolutionary functions completely follow this poly-algorithmic approach which I've previously described. So this is in another paper basically where I talk about evolutionary VTS, so insertion and deletion in VTS. Talked about that at another conference. Strategy options, there's quite a few. I might sort of streamline this a bit because it's fairly hefty as it is. But currently that's the strategy that you currently have to choose from. There's a sub-package called QuantifierTools. It produces it. So these Tarski formulae are probably something that most people are not privy to. So QuantifierTools sort of gives you some things to work with those. So it will do alpha conversion on non-prenex formulae. So that basically removes ambiguities between variables in quantified formulae. Negate formula is fairly self-explanatory. Most problems won't really manifest in prenex form, or well, they won't even manifest necessarily in polynomial form. So if you have some science problem which manifests with rational constraints like this, f over g, then it will convert them into the same sort of problem for an actual Tarski formula, which basically means everything is polynomial. So there's a function to do that. Then there's a conversion to prenex form routine as well. So probably right now is where I show you, this is Maple 2056, after quantifier elimination has been released. So exports to quantifier elimination, basically what I talked about. Got this sub-package. And can we solve a quadratic? Yes, we can. That's fantastic. And then here I'm going to embarrass myself with this is the mechanics problem from earlier. If you do the quantifier elimination problem on that, you get something very messy, right? So if you actually look at that paper where the examples come from, then I think the answer is basically that N1 is like 475 over 2. It's bounded by that. And then N2 is something else that you could get from in here. But this is ridiculously messy just because this is all done by VTS, and VTS is quite poor at simplification. So really, this needs to be simplified, right? Apologies if this is so big, but yeah, so this won't all fit on the page. Witnesses. So that's what a witness looks like, right? So if I want to ask, okay, assignments of XYZ such that XYZ is more than 0, that's a satisfying assignment, right? That's the idea. And if I really want, I can ask for more, right? So that's the complete covering of all the witnesses that will solve that problem for you, right? And I can even coax out a situation where you get some unevaluated problems given back because they weren't processed as part of a tree because you didn't need to, right? So it'll give you these unevaluated calls back. Going down some more witnesses, right? So just going to check that's a satisfying assignment. It is. Ditto for just CAD. Yeah, cool. Evolutionary calls. So this should explain what they mean a little bit more. So I'll also demonstrate info level as well a little bit. So if I ask for a third output argument here, it's going to give me a little object that I can pass into a next routine. So here what I'm saying is, okay, I did this, but actually I can weaken my, I mean, obviously this is a completely degenerate sort of problem, but if I want to delete the first constraint, so as part of this and, this xy 0 equals 0, then I get back this, right? So yeah, clearly if I choose something a little bit more than 4, then that was satisfiable without this, right? And then if I add it back, I can add it back. So you can insert formulae likewise. And then, yeah, in terms of strategy, so this is basically the intersection of a ball and a circular cylinder. This is an algebraic geometry problem, really. If I do partial CAD on that, I can choose a variable strategy there. So I've chosen the greedy one. And then, yeah, it says true. So here it did x, z, y. And yeah, checking that's all right. That's completely fine. And then I can choose another variable strategy. And there it did y, x, z. And then lastly, if I specify completely my own, so I don't like any of the inbuilt ones. I can specify ZXY, it does that, and these are all fine, hunky-dory. So this is really just demonstrating the input and output semantics of quantifier elimination. So it gives you witnesses and it gives you the quantifier for the output, right? And going back to the slide, so I'll just wrap up now, basically. So some preliminary benchmarks from the underlying new CAD implementation. This is a little bit small. Let's see if I can blow it up. Basically, mine is better. I do have than regular chains, and so yeah, this is tested against regular chains and
CAD of regular chains.
just cylindrical algebraic decompose. So stock.
So that means the projection lifting algorithm.
Yep.
Yeah, you should use the latest one.
Yeah.
The one is much faster.
Okay. The latest one being like on the web, not native.
Yeah, it's available on the web for you.
Right. Yeah, to be fair, it's tested against native, yeah, that's a good idea, actually. I should do that. Why won't this? Oh, going. Yeah, so there are a few examples, only one, actually, I think, here, where the others did better than me, but I'm a blue and orange bars. The orange bar, I think, is with equational constraints, which is this optimization I'm talking about, but you can turn that off. Yeah. So most of those examples are from my predecessor, if you like, David Wilson, his QE database. Let's get this back in, right? Yeah, so basically what I need to do more of is I need to investigate these strategies a bit more. I need to benchmark better, according to Mark, and test a bit more, bug fix, ready for release. There's also this other sort of relatively new thing called new CAD, which might be interesting for QE. And yeah, please talk to me about any more applications of QE or any suggestions for this package in general, if you have any. That's it. Yeah.
Regular chain has also QE.
Yeah. So, but that was just benchmarks.
No, I know, but I think when you have listed different software where
Yeah.
QE, you could have mentioned that regular chain has QE. It's not.
Yeah. So that was
He has it for years.
yeah, that was QE software. That was
And it has a Q method which is based on the incremental CAD.
yeah.
And that's also
Yeah, I mean that's interesting as well. That's interesting as well because if you want to, you can do pure incremental CAD from mine just using CAD data objects. So that's good. So I should test that, which I haven't. Yeah.
I've seen a function named parcel cylindrical algebraic decompose.
Yeah.
Does it mean that you compute only the cells of highest dimension or just...
It means you stop CAD once you've deduced a quantifier-free answer. Yeah. So this down here, I gave it QE problems, but
Okay, nothing to do with the dimension of cells.
no. But there is also just this is my cylindrical algebraic decompose, has the same name as a regular chain's native function at least, which does a pure CAD, but I don't actually know what I want the output of that to be yet. So currently that'll just give you the number of leaf cells basically, but I need to decide what it should actually do. Yeah.
Which part of your algorithm do you think is mostly responsible for speeding up the computation? Do you think the projection?
Well, yeah, so projection is only relevant when you start a CAD. Yeah. I mean, as far as we know, we have the best possible projection, in the Lazar projection. So for me, I'm not particularly interested in that specifically. I'm interested in hybrid, right? And I'll admit that right now I think there are some deficiencies in hybrid because I was actually, I call it hybrid, sort of, the poly-algorithmic stuff. So you switch the passover from VTS to CAD, yeah? I think right now I've been too pessimistic about how that's handled, and I really need to work more on the implementation of trying to traverse the tree depth-wise via VTS, switch it to CAD, and then work from there. Yeah, that's where the speed up has got to be. It's a research question in itself. I don't know completely if it will work, but in the worst case, there will be the implementation, or I'm already working on it basically, the implementation where you just collapse the entire VTS tree to a QE problem, give that entirely to CAD if hybrid is undesirable in some way.
And you pick the ordering given by the default functions in regular chains, is that right?
No, currently not. So currently the CAD orderings, Brown, SOTD, NDRR, I guess you know these, UPS basically, and something called greedy ordering.
So these are the ones you're using.
In CAD, yeah.
And so you tried with several heuristics, or you use the same one for all of them? Or?
Currently it defaults to brown because, you know, even from your work, brown seems to just be pretty good across the board, right? So currently it defaults to brown. I haven't completely benchmarked in terms of what's best, you know, VTS and CAD. I imagine it'll be brown for what's there, but yeah.
You have a strategy for choosing the ordering, but do you have a strategy also for choosing the cells for the listing?
Yeah, so that is stock standard, comes out of the partial CAD paper, if you know, Hun Hong and yeah, it's completely that. So you get to pick between highest level, least index, and what the rest called, I don't remember. But there's all those, right? So there's like 4 or 5, yeah? It's just for ones from that paper, yeah. I think it defaults to what they said is best to default to, which is highest level, least index, right? Yeah.
Thank you very much, Zach.
Cool. Thank you.